Last time we talked about how to classify triangles using attributes. One of the ways was to look at the number of congruent sides. If 1 a scaling, 2 an isosceles, and 3 an equilateral triangle. By observing pictures, I also pointed out that we can classify them by the number of congruent angles, which shows there must be a strong link between angles and side length. Before getting into the angle and sides, I want to talk about how to name things. If you recall, this was the picture I used to show that the sum of angles inside a triangle is 180 degrees. You probably have noticed that I used letter A, B, and C, and for congruent angles, I used A prime and B prime. As for names, there's nothing special about A, B, and C. As long as they are distinctive in your picture, they serve the purpose. If you want to, you can start calling X and Y instead. Or you can call them latte and mocha. The reason I call them A prime and B prime is because A and A prime are congruent and B prime are congruent. I wanted to reflect that they are same in the measurement by making sure the names are similar. One philosophy is to make sure good names show pattern apparent to the reader. As for a triangle, the usual convention is we use alphabets for angles, since you don't want to write latte and mocha 5 times, and use the same letter for side opposite angle of interest. So in this case, the bottom side would be called B, just like the angle on top. For today's lesson, I'll be primarily using anglex to explore the relationship between angles and side length. Now, anglex come in a variety of colors and length, and as a reference, here's a table of length. One of the activities for the lesson will be filling out this table using anglex. Notice that we're using the same custom I just talked about earlier. For a triangle ABC, the side opposite to the angle A will be called A, except that this is in lowercase. If you haven't done it already, try building various triangles on your own and come back to the video. Now, I started making equilateral triangles using purple since I like purple, and also purple one seems to be not too short, not too long. If you're new to drawing legs, you can simply snap to connect legs to form an angle. Since I started with a purple equilateral triangle, I decided to reuse purple sides and build different isosceles triangles using different colors. The one I couldn't work out was the red, since it seemed that the red leg was too long to form an actual triangle. We will come back to this case later. But for now, we'll just draw the red out of the way and think about orange, green, blue, and yellow. As it turns out, if you measure the angle opposite to the yellow using the protractor, one made with a yellow leg turns out to be the right angle. You can see me snapping the protractor to the angle that I'm interested in, and I'm going to align the protractor so that 0 is on the one of the leg, and you can see that it's 90 degrees. So a thumbs up for that. So here's the table after measuring each angle for all triangles I just made. Take a moment and observe the pattern here. As you can see, an equilateral triangle has 3 congruent angles, as we expected, and we have physically verified that any isosceles triangle has 2 congruent angles. Not only that, we can see that if you have 2 congruent angles, you have 2 congruent opposite sides. Comparing along triangles, we also notice that when the angles go up, for example, here I look at angle C and it goes up from 41 to 120, the length of opposite side C, that is starting from 5 and going all the way up to 12.24, is also going up. This seems worth investigating. Since I only made an isosceles triangle, I decided to make 3 different scaling triangles and measure their angles as well. When sorted so that reds are always A's and blues are always B's, we can also see the same pattern, that when the angle goes up, so does the measurement of the side opposite to that angle. So this is not just about isosceles triangle, but it seems that this pattern is for every triangle. What else do you see for a scaling triangle? For the angle C, it does seem that it can't go beyond 50 degrees because we chose the other side to be shorter than the red and blue. Inspecting closer, focusing on, say, the last triangle, we can see that one with the largest angle, that is A, has the side that is the largest, that is side A, whereas the smallest angle, C, opposite to that is the shortest side, which is C. So let's make these observations into a neat summary. For many triangles, fixing the side length for other 2, when the angle goes up, the opposite side length goes up. And when the angle goes down, so does the length of the opposite side. What else do we have? Inside a triangle, largest angle corresponds to the longest opposite side. And similarly, if you have the smallest angle, the opposite side is the shortest among 3 sides. With this observation, let's look at a problem. Given 2 triangles like this, which segment in the figure below is the longest? Let's think for a moment. We can try to use observation number 2 involving scaling triangles. Focusing on the right, on triangle BCD, the triangle with 56, 52, and 72 degree angles, we can observe that the segment BD is the longest among 3 because it is opposite to angle C that measures 72 degrees, the largest among 3. But looking at triangle ABD, or triangle on your left, AB is the longest since it is opposite to 65 degree angle. Now since the segment BD, one in green, is still part of this triangle ABD, we know that the one in this yellow segment, that is segment AB, is longer than BD. Combining these 2, we know that among all the segments, segment AB is the longest. Now lesson 7 video ends here. If you want to learn about Lesson 8, continue watching. Now let's take care of that triangle we couldn't build. With two purple, it just didn't work. It looked like if I tried to snap it, it collapsed into a straight line, not making any triangle. Since oranges are shorter, trying to build a triangle using two orange legs with red would not work. And by the similar principle, orange and purple doesn't work, whereas blue and purple works nicely, as you can see on the top. Try working with legs of different colors and see if you can find a similar failure, filling this table out. Here's what I did just a few seconds ago with a successful triangle as a comparison. What we observed was that the purple set that measures 7.07 centimeter were not long enough to match to the length of the red one, which was 14.14 centimeters. Also, the orange one, measuring 5 centimeters each, was not long enough compared to the red one, again 14.14 centimeters. As a comparison, if I did the purple one with a long blue one, that is 12.24 centimeters, this seemed long enough to form a triangle. To get that notion in my mind, I added the length of B and length of C and tried to see some comparison here. The successful case, 19.31, is obviously longer than 14.14, whereas these three cases, the failing cases, seems to be smaller or equal to the 14.14, the length of side A. So from these table entries, we figured out that the B plus C, the sum of the lengths of other sides, needs to be greater than A. To test it out, I constructed three other triangles, one with red, one with green, and I filled out the entry to see if this hypothesis is true. So I have green measuring 8.66 centimeter, I have red measuring 14.14 centimeter, and some other size measuring 12.24, 7.07, or 10 centimeters. By checking the algebra, the longest side, 14.14, is smaller than, say, 8.66 plus 10, which adds up to 18.66. So it seems that to form a triangle, I would need two sides adding up and being greater than one of the sides. So how do we explain this physically? Let's start building some intuition here. For one thing, let's go back to building a triangle. I said a few lessons earlier, in order to make a triangle, I would have to start with a long segment and make two turns. We can ask what happens when two sides are too short. Well, in order to make a return, you will need to travel back as much as you traveled away. So calling this long segment A and the other two B and C combined, which is the return trip, needs to be as long as A. So in ordinary language, the longest side needs to be shorter than the sum of two other sides. So in this case, if you have 5, 12, and 6 centimeter sides, they don't form a triangle because obviously 12 is greater than 5 plus 6. With that observation in mind, let's try to figure out this mystery here. Suppose I have two mystery triangles whose side A measures 8.66 centimeter, side B measures 14.14 centimeter, just like the triangles that we observed previously. I don't know the length of side C in this case. I can ask for mystery triangle number 1, what is the shortest possible length for side C that connects these two sides? I can also ask the longest possible C that connects these two sides to form a triangle. Take a moment and think about the approach in this case. Should I use the difference? Should I use the sum? Is there some other mathematical formula that I need to be aware of? For a starter, I know that the longest side has to be shorter than the sum of the other two. So for the first problem, I can see that since I'm looking at short side C, B needs to be shorter than sum of the other two, in this case A plus C. By throwing that into an actual inequality, 14.14 is less than 8.66 plus C. So we're actually looking at the difference, that is 5.48, being smaller than C. So C needs to be at least 5.48 to form a triangle. Now what about the longest length here? Since I'm looking at the longest possible side, C will be the largest. So we need C to be smaller than the sum of other two, in this case A and B. So C is less than 14.14 plus 8.66 means that C has to be less than 22.8. So let's summarize what we just learned by applying the relationship to a triangle whose side length is A, B, and C. How can you write this as a mathematical formula? Using an ordinary words, we know that the longest side needs to be shorter than the sum of other two sides. Now this is descriptive enough, and often this is very easy to teach, especially when you're teaching with explicit numbers like 16 centimeters, 4 centimeters, and 2 centimeters, because students will have easier time understanding actual length. But the disadvantage of this way of describing is that we don't know, when using symbolic mathematics, that which one is the longest and which one is the shortest. So let's scrap this out and try to think of it this way. If A is the longest, we need A less than B plus C. If B were to be largest, B needs to be smaller than A plus C. By the same logic, if C were to be longest, C needs to be less than A plus B. Combining these three, we can say, in simple words, all sides needs to be smaller than the sum of the other two sides. And that is the way to describe this using inequalities.